for coming back after lunch. It's always a good one when we see that happens. So this afternoon we've got a couple more presentations and also our round table discussion. I'm going to hand over to Dr. Andrew Wright, who's involved here at DMU and going to run through about decarbonising heating and use of heat pumps in school.
Right.
I shall leave you to.
Thank you very much. Okay, so hello everyone. So I'm going to talk about this, and not for very long. I'm hoping to have time, but plenty of time for the discussion after that. So, decarbonising heating and the use of heat pumps. This is just my sort of personal view on where we are at the moment with all this, with all the fuel prices and everything else. So I've been here quite a long time. I have previously worked in industry and done design as well a bit, and I teach on master's courses and have PhD students and things on this kind of topic. So first of all, drivers for school environments. I guess from an engineering point of view, it's to provide comfortable, well ventilated spaces, but obviously there's all the other design stuff. I had an interesting conversation last night about making spaces interesting and so on. That's all the architecture. I'll leave that to you lot. But it's very much about education and providing a good environment. But we also have to think about cost, of course, the cost of fuels, which have gone up hugely in the last year, and the capital cost of work. There's also a massive, obviously, carbon reduction agenda, aiming to get to net zero by 2050. And there's also future proofing for energy supply and climate change adaptation, which perhaps will become really much more important in the next 50 years or so, as we apparently are going to move to a much warmer, more heat waves and things. So if we look at UK emissions, it very roughly divides into roughly a third for buildings, a third for transport, and then the rest is made up of industry and land use and so on. And then if we take the buildings part, the vast chunk of it, this segment here, is for heating, 23% of the total. Most of that is homes, but then we have public, which includes schools. So that heat is a really big part of our energy system, a really important part of it. I think people perhaps sometimes think about electricity too much, and they forget about heat as such a fundamental part of our carbon emissions and energy. If we look at our progress to reduce carbon emissions, it looks quite good. If you look at the chart, and it's all based on 1990 values, so we've come down fairly steadily by a sort of 45% reduction to 2019, and we have targets of 68% by 2030, 78% by 2035, and then 100% reduction by 2050. If you look at the curve, you might think, well, you can just carry on down that trajectory, and it's all kind of just carry on and we'll get there. But actually it's much harder than that, because most of that reduction has been going from taking out the coal generation, massive increase in wind and also solar, and a general improvements in efficiencies in things like gas boilers and lighting and things. We've probably done all that stuff, a lot of it, and so this extra, down to zero, is a huge challenge. And one of the really big challenges is to decarbonise heat for buildings. It's such a big chunk of our emissions, and that is really not easy, because we have a set effectively almost all buildings are heated with gas, and the boilers are pretty efficient now. So we need to go beyond that, to get that emission down. Quick plug for the TM57 integrated school design document. Recommend it if you're a designer. Lots of interesting stuff about services and energy and design. I'm a member of the school design group. So classrooms are quite unusual spaces in terms of, lots of things. They're high density, a lot of metabolic gains when they're occupied, have a high ventilation demand as a result, need to keep CO2 below 1,000 parts per million to, provide a healthy environment. They're unusually flexible use of spaces. They're not like as most spaces which just have one function. They have lots of different functions in a school. And they're usually day-lit, so that increases challenges for heating and so on, overheating. Generally, or very often, naturally ventilated. It's a big debate about whether that's the best option in terms of energy, but they very often are naturally ventilated. And they often open up to external spaces, play areas and things, which all of that is quite challenging in terms of making heat and reducing your heat demand for that space. And also external noise may be a problem in some urban sites. Finally, wall space is at a premium in classrooms for displays and so on. Again, that's a bit unusual. So you don't want to have massive radiators everywhere taking up lots of wall space. I think fabric first has probably was very much a mantra for a long time. Don't worry about the energy, just get the fabric right. But that's perhaps not entirely realistic. New build characterised by much reduced heat loss and infiltration compared to the old stock. So insulation means your heat loss is way lower than old buildings. There are some passive house schools which have performed, I think, some very well. Most likely to have mechanical ventilation, or at least quite a few. In theory, there's a low heat demand, but not always in practice. There are lots of issues around commissioning, and the soft landings scheme to try and sort of make that process better and inform occupants and things is important. And there have been cases of overheating and ventilation not always working terribly well. Whereas the older schools have much higher heat loss, heating dominated, really deep refurbishment, as you know, it's really expensive. And so I think we need to take a sort of a lifetime analysis of the capital and operational costs. You can't just say you must get the fabric right down to really low levels, because it just probably isn't practical or economically feasible. So it may be other energy solutions are so in the balance there as well. So a few years ago, this was a situation, gas was cheap, seen as a low carbon fuel at the time because it was replacing coal and oil and so on. It's easy to install, and so it's really, it's a perfect fuel in many ways, virtually. It's no local pollution, and it's really was the obvious choice if you had a gas grid. Whereas electricity was high carbon, was expensive, again, no local pollution, but not really seen suitable for heating most in general. If we move to where we are now, it's not really seen as low carbon. Well, it is a lowish carbon fuel, but now we're trying to move away from fossil fuels. So it's effectively, it's a carbon fuel, so we're trying to get rid of gas. It certainly isn't cheap anymore, thanks to Ukraine and other factors. Those still apply, of course. It's no longer the obvious choice on the gas grid. If you're trying to decarbonise, we're looking towards heat pumps. Electricity is no longer high carbon. It used to be about 0.5 kilogram per kilowatt hour of electricity a few years ago, compared to gas, which is about 0.2. Now they're about the same in terms of kilowatts heat. Still expensive. And maybe it may be suitable for heating in the right circumstances if we use heat pumps, and we can also generate something on site, although that doesn't tend to coincide with when you need heat. It's mostly the summer, often when the schools are closed and so on, but we can put solar panels on. So what is a heat pump? Very simply, something that moves heat from cooler to warmer. So it's going against the natural flow from warm to cool, the opposite. It's kind of breaking the natural flow. This does require energy input, usually in the form of a compressor. It's funny, people struggle with heat pumps, and yet we're quite used to the idea of heat engines. Many of us have cars or motorbikes or whatever, and that's a heat engine. So you use heat in the process of transferring heat from one high temperature to low temperature, you can generate power. So what a heat pump is doing is reversing that process. So you're using power to move heat. It's kind of scientifically the same thing. And we can either extract heat from space to the outside, which is cooling, or air conditioning, refrigeration, or we can extract heat from the outside to space or to domestic hot water, which is heating. And that's usually called a heat pump. And it's the same, basically the same kind of technology, but we tend to use the heat pump label tends to mean heating, and the air conditioning label tends to mean cooling, but it's effectively the same, just in the opposite way. Now, thermodynamically, there are limits to efficiency. You can't move heat for nothing, and there's a Carnot efficiency, which is a calculation to say how much the minimum energy you need to move a certain amount of heat through a certain temperature difference. Typically, the heat transferred is about 2 to 4 times the energy input. The energy input being electrical, normally it's a mechanical process. You could use any kind of mechanical device, but an electric motor is the obvious, the compressor is the obvious way to do it. And this ratio is called the coefficient of performance. And that's basically why electric heat pumps are viable, because of this ratio not being 1, it's a lot more than that. So you can actually move a lot more heat than the energy input. You're not creating energy, you're not cheating physics, you're just moving heat from one place to another. So why heat pumps for heating? Well, once you decarbonise your electricity, heat pumps become low carbon. Current electricity, grid electricity is about 0.2 kilograms of CO2 per kilowatt hour of electricity. Once you've applied that ratio, let's say of 3, it depends on various things, but let's say it's 3, then it's 0.2 divided by 3, that's about 0.07 kilograms of CO2 per kilowatt hour of heat, right? Compare that to a gas boiler, which is about 0.2 kilograms of actual heat, then you've got an efficiency of 90% maximum. So you're going to add a 10% to that, so it's about 0.22. So it's about a third the carbon content of burning gas in the boiler, which is a complete reversal where it was some years ago when we had high carbon electricity. And electricity has the potential to decarbonise further with more renewables, nuclear, less and less gas. We're still building huge wind farms. Solar is becoming quite a significant contributor as well. It can be up to 25% of demand on a sunny day. So this is a schematic of a heat pump. So imagine you have a cool fluid going through the evaporator. That's picking up heat. That can either pick it up from the room for cooling, or it can be picking it up from the outside to heat the building. And once you compress it, you heat it up. It's like if you pump up a bicycle tire, you feel it getting warm. Because of the compression, you're increasing the temperature, and that's where the energy goes in, and that's the clever bit that sort of breaks the usual flow of heat by heating it up. You then extract the heat for example, into the space, and then when you expand it, it cools down again. That means it's cold going through the evaporation, and then it's cold to pick up the heat, and the cycle goes round and round. And you can either this is heating the space from the outside, or it's cooling the space and dumping heat to the outside. And the closer the temperatures are, the more efficient the process. That's really important. That COP value of 3 or 2 or 4 is going to be bigger if these temperatures are more similar. And that's important both for the internal emitters in the space and also the external source of your heat or cooling. So just to look quickly at the various types. So an air source heat pump, this is a typical unit. You've probably seen these around, just like an air conditioning. Well, it's the same thing really. This is a dumping the heat, or either extracting the heat or collecting the heat, depending which way the ground is going. There will also be a heat pump, which looks like similar to a boiler, really, big white box, probably inside the building. It's the cheapest, the simplest solution, one favoured by in the housing market at the moment. Not very efficient in cold weather, because at low temperatures that delta T becomes bigger, hence it's not so efficient. And also, when it gets very cold and we have a relatively humid climate, even in the winter here, you get icing on the device, and then that means you have to somehow get rid of the ice, reverse the heat pump or something. That reduces the efficiency, and also the ice just clogs it up and stops the airflow. So you probably wouldn't size it for the maximum demand of sort of -5 or something. You might size it for lower demand, then have some sort of boost or top up of gas or some other system. And they do generate some noise, of course. There's a noise of the fan. You can use them reversibly for cooling. If you have an air delivery system, you can't really cool the space with radiators because you get condensation and it's not going to work. So if you have an air system, then you can use that to cool the space just by reversing the system. Another option is ground heat exchangers. And this building we're in now, which is a picture of it there in that corner, uses ground heat exchangers for heating and cooling. I forget how many loops there are. There's quite a few loops in the ground outside. So these are more efficient because the ground is generally less cold than the air in winter. So the ground might be at say 11 or 12, when the air might be at sort of 0. Therefore, you get the delta T is smaller. Therefore, the efficiency is greater. And similarly, in summer, day like today, might be 20 outside, but the ground will still be around 12 or something. That means you can get rid of heat more efficiently into the cool ground. And it's more stable temperatures. Typical boreholes of 100 meters deep, quite deep. And big cost really is the drilling. You have to drill those holes, and that needs specialist equipment. It costs a lot of money. A major part of the cost, and it's not always possible if you're on granite or some dodgy soil or something. Then it may not be possible. In London, they have to worry about drilling through tube lines as well and other things. So it's not always a solution, but effectively, it's the more expensive option that works better, to put it very simply. Although, again, you are committing yourself, once it's in the ground, it should be there for decades, whereas with an air source, you could put an alternative in 10 years' time, quite easily. So it's sort of, you're committing yourself to it more strongly. Just that this is a bit of fun, really. This is it's called the Solar House in Great Glen, which is a village southeast Leicester. And this was a project we had with a developer where he put, I think it was 38 panels on the roof, PVT, so it's collecting heat and electricity, and drilling quite shallow boreholes, 1.75 meters, in the footprint of the house, and then so you use the solar heat to put it into the ground, and then you extract it in the winter for heating, and it does work. I mean, I wouldn't. Yeah, there isn't a lot of very clear evidence, but it does seem to work reasonably well, and we have a couple of PhDs on this as well. So it's just solar-assisted ground heat storage, which is another option. The problem you can't obviously use it for cooling because you heated the ground up, so it won't be very good for cooling. And then water source heat pumps. This is the river just down that way, runs alongside the campus, the River Soar. It obviously very location dependent. You need a load of water, a river or a lake or something. You get really good heat transfer because it's a fluid, it's got very high heat capacity, so you can transfer loads of heat easily from water to your system. And you again have stable temperatures similar to the ground. In a way, again, a really good solution if you've got it. And DMU is actually looking at the feasibility of using the River Soar water for a heat pump through its buildings. Most of it have gas boilers. 1 or 2 have biomass as well, but this is could be a solution for DMU. Then a bit about the internal heat emitters. Remember this delta T, you want to minimise it, so you want to have a low temperature delivery as far as possible in the space to keep that temperature low, and that's one of the big challenges. So you need larger surface areas to deliver the same amount of heat into the space. You may not be able to retrofit to existing radiators, they're just not big enough to deliver the heat. Underfloor heating is a good option for schools. Many schools have done this. Preferably not carpeted, because that will create insulation and reduce the heat flow. And there are obviously limits to temperatures and so on, but it is quite a good solution which it works quite well with heat pumps. Or you can use air systems, which you can also use for cooling. Again, air is obviously low temperature delivery, so it's got a smaller delta T. I'll just briefly mention a few other options. Combined heat and power, there was a lot of interest in that some years ago. The government saw it as a sort of a low carbon way of getting electricity and heat at the same time. I think that's largely disappeared now because it's still a carbon fuel. Your carbon emissions will be relatively low because you're burning gas to generate power and heat, so it's probably out. Another one is biomass boilers. Many schools have installed them. Obviously, there's quite a commitment to storage space and logistics of having a lot of bulk of fuel on site. But some work well. There has been pollution issues around, particularly urban areas, London and so on, having lots of these. If they're not properly designed and maintained, then they may create air pollution, which is not good news. Particulates particularly. Hydrogen there's a lot of talk about hydrogen, and hydrogen is a vector. It's just a way of moving energy, really. You can't mine hydrogen. You've got to create it somehow. The thinking is you generate it with electricity, by electrolysis, and then you have hydrogen, and it will be a very simple, practically very simple solution to pipe hydrogen around the gas network instead of methane. So it's zero carbon because it just creates water when you burn it. But making a load of hydrogen is not easy, and it's much less efficient to use electricity to make hydrogen with a significant loss of energy, and then to compress it with additional energy input, and then decompress it, and then burn it in the boiler, which is 90% efficient. You've got all these losses in the chain for hydrogen, which make it. I mean, it'd be better to use direct electric actually, because that's just at least it's 100% efficient at the beginning. The issue, of course, is storage, because you could potentially store large amounts of hydrogen, and when you can't store large amounts of electricity, really, at the moment, although batteries are getting better. So I think hydrogen is probably overhyped. That's my personal view. It may have a place, but I don't think it would be practical to convert our massive gas use to hydrogen. You have to create huge amounts of hydrogen to do that, whereas you can use electric heat pumps much more efficiently in terms of kilowatt hours of heat per kilowatt hour of power than making hydrogen and then burning in the boiler. And then there's direct electric, which obviously has its place. If it's a super low energy building, it might be quite sensible to have a direct electric. Really simple, really easy to control, very cheap, but it's not as good as heat pumps. It's a 1-to-1 ratio. Okay, that's me done. So I open it up to questions and discussion. Yeah.
Yeah, just interested in the sort of whole life aspect. So it's like comparing ground source and air source. Just wondering what the kind of embodied carbon implications would be for those kind of two technologies, and whether the ground source, investing in those big boreholes that presumably could be around for a good few years, would be a better investment long term than an air source, which you might have to replace every 50 years.
Well, I think that's a big question, and obviously the cost of finance is another issue. So you basically have a high capital cost with low running costs with the ground versus the air, where you've got high running costs. And I can't answer that question. In terms of embodied carbon, I suppose the ground would have higher embodied carbon because you've got all the drilling energy, and then you've got quite a lot of pipes going into the ground, but it's probably not huge. It's a load of plastic pipe basically and some drilling. But whereas an air source is a fairly lightweight box, a big family. So yeah, but I don't think that'll be. I would have thought the carbon savings would be outweigh the embodied carbon for the ground. That's my guess. Yeah.
I mean, my view, and I've looked at it, is when you invest in ground source, you're investing in infrastructure that's going to be about 50, 100 years.
Yeah.
With air source, you've got something like, say, that could be replaced within 10, 20 years, and you're probably going to be packing up around 15, 20. And it's understanding that water-based compressors tend to last longer than air ones.
Right.
Is my experience.
Yeah. Yes.
Would ground source heat pumps work with MMC, with modular?
Yeah, I mean, it doesn't. It's agnostic about the building, really. The most important is to have an efficient building. I didn't really say this, but heat pumps are fairly expensive, and going back to fabric first, particularly the new build, if you can get it really low energy demand, then you can have a small heat pump and it doesn't cost so much. But the MMC, yeah, I mean, it's probably better actually. It's a really better air tightness and better, performance, more predictable performance. Yeah.
Just a question. The efficiency of PV is around 22%. And obviously, since the 1980s, that's increased up to about 2 to 3% over the course of 40 years.
Yeah.
And the core efficiencies, air source and ground source, from 2, 3, 4, 5. I'm wondering if that's going to be accelerated or it's going to be a very slow creep in your view.
I think it'd be incremental. There are thermodynamic limits. The Carnot efficiency is easy to calculate based on the delta T's. You probably can't. It depends on the conditions, but you probably couldn't get up to sort of huge numbers like 10 because it's just not thermodynamically possible. We've actually got a research project with Imperial College and Leeds and Cambridge at the moment. We're looking at partly using piles for the ground source, but also looking at different kinds of grout and concrete mixes and so on. Because one of the challenges with ground source is just getting the heat flow from the pipe into the ground, or the other way around. We had this with one of our research projects here. That's a constraint. We had the PV panels on the roof. You've got plenty of heat going around, but then the water was coming back almost the same temperature because it just wasn't getting into the ground fast enough. So there's lots of things you can play around with the diameter of the pipe or the conductivity of the grout or in the soil, whatever. So it's a bit of a constraint which you don't really have with air because you just have a bigger house. Yeah.
Interested in your experience on the water source, because there are restrictions of what you can put in, however you affect water courses. Previous experience having owned a water mill, 1,000 years old, owned the river but not the water in it.
Right.
Yeah, so obviously there's restrictions about any affecting water flow.
You have to get permission, don't you, to use it?
Normally you have to create your own, in effect, diverted channel with permission.
Yes, it will be pumped up from the river and through a heat exchange and back. It wouldn't just be sort of in the river. Yeah. It's quite shallow as well, actually. Yes.
What's your experience of creating hot water for commercials? I'm not talking about heating and resin, I'm talking about hot water for washing and how heat pumps work.
Hot water is, I didn't really talk about hot water, but yeah, heat pumps are being used for hot water. Because the delta T is much bigger, if you're heating the water to 55 or something, that's going to be a lot more less efficient than just heating it to 30 or something for a space. But there are heat pumps which will do it. You do lose some efficiency, but it's probably a sensible option is to use a heat pump for hot water as well as space heating. Although you probably use solar possibly as well, to boost that. I don't have any practical experience of it. But certainly they're beginning to use it domestically now.
It's just with regards to sort of the overall longevity of the using sort of heat pumps. Conscious where using sort of various refrigerant gases, how sustainable that would be, given that the refrigerant gases are also a global, have a global warming potential element on that, sort of in terms of sort of looking forward in terms of designs and sort of selections of sort of gases for this. What would be sort of the ideal gases to have set up for use with different process plants? Has there been any knowledge or experience or research into that?
Not my area, but there is a lot of work going on refrigerants. There are now zero global warming potential refrigerants, such as ammonia, carbon dioxide, and so on, which have their own issues. But I think we're moving away from both the ozone depleting and the global warming depleting or global warming causing refrigerants. I mean, the actual your heat is going to go through a circuit with glycol or something in it, so that's sort of separate. But it's within the heat pump itself, you're going to have the refrigerants, and there is, I think, a lot of development going on with refrigerants at the moment with heat pumps. Yeah.
Just thinking about where application of heat pumps to new buildings, good insulation, great. Is trying to apply to existing buildings, which you may not have the capacity to be able to change the emitters, etc. It's the viability of the hybrid systems to actually use maybe the heat pump to produce the water up to such a temperature, and then sort of use another source of heat inductance, whether that's becoming a more viable way to go in buildings where you can't change emitters or improve the heat balance.
Yeah, I think I might. It's not. I'm not an engineer. I don't design systems, but I would have thought there would be potential for hybrid systems with gas boilers, for example. Particularly because you don't want to oversize it for the 3 days of the year when it's really cold. Whereas a gas boiler, it doesn't matter if it's oversized so much, but if you could somehow use existing boilers to do maybe 10% of the load, and then the rest is heat pump, I think that might be a way forward. I don't know about the engineering or where other companies are with it, but to me that makes some sense. Although obviously it gets complicated to control when you start having lots of valves, and the actual algorithms to control, they're not that straightforward. But yeah. Yes.
Just a general comment. I think that unfortunately the heat pumps, the implementation has been a bit challenging. And this idea that you can just change the gas boiler to heat pump and everything will be fine is partially the government's fault, I think. There's still just being unknown. And people have really got to look at their system temperatures, otherwise it would never work. That's not really a question. Comment.
Yeah, I think you're right. I think the supply chain is still quite, new, and so domestically. I mean, I've got a 20-year-old house with a 20-year-old gas boiler, which isn't condensing. I'm kind of thinking, well, shall I change it to a heat pump? Would I trust it to actually work? Would what if it doesn't work? Would my wife let me spend all that money? I'm not convinced yet that it will be a good option. And also they might be a bit more efficient in 2 years' time. So it's really difficult. Domestic across the board. Maybe it's harder for domestic because it's a harder market to sort of influence, and you need a really well-established, reliable supply chain. A bit like electric cars. It's taken a long time before they're really established. And I remember riding in a Toyota Prius in 1999. That was 23 years ago, and now they're pretty standard hybrids, but it's taken a while. Yeah, I think that there is a confidence issue in it. Yeah, I have no idea what the time is. How are we doing?
No, you're okay. Got a couple of minutes.
Okay. Yeah.
I think one of the other points perhaps hasn't been raised is particularly the retrofit context is grid and site capacity, because changing from gas to all electric is going to clearly increase your requirement, and we've had situations where just because of those constraints around cycling grid capacity just doesn't become viable.
Yeah, I didn't talk about the grid, but if you think about the earlier chart of the emissions, you've got a third transport, third buildings, which is mostly heat, mostly gas, and a third industry and so on. So if you're going to shift most of your transport eventually to electric, and most of your heat to electric, that's a huge increase in electricity demand in terms of volume and also in terms of the grid. And yeah, that's a whole new thing, is the grid. I had smart meters fitted on Wednesday in my house, and we're all moving that way, you know, having more dynamic tariffs and, you know, two-way control for your appliances. They turn off when they can to take the load off the grid. So that's another big challenge. I think it's doable, but I think it's you know, it's another big thing. Yeah.
Yeah, I mean, it's just really that early key piece of work around the DNO that needs to be done before you think about, you know, sizing the feed pumps, just to understand the viability.
Yeah, it's a good point. Yeah.
Okay, any further questions at all? Fabulous.
Right, thank you.
Very much, Andrew.